Okay, here's another related rates example problem. This one is from worksheet, what's called related rates day 2 or worksheet number 2. I'm going to do number 3. It says, and this is a separate piece of paper I'm going to use this to actually work on, but the problem says, water is pouring into an inverted cone at the rate of 3.14, basically pi cubic meters per minute. The height of the cone is 10 meters, and the radius of its base, which is really at the top, by the way, because it's an inverted cone, meaning it's like an ice cream cone, it's upside down. The radius of its base is 5 meters. How fast is the water level rising when the water stands 7.5 meters in the cone? Now, this is a large cone. 10 meters is like more than 30 feet. So this is a cone that's more than 30 feet tall. It's like taller than most of your houses. It's a very, very large cone. 3.4 cubic meters per minute of water. So imagine the pi cubic meters per minute of water. Imagine a cube that measures 3 meters by 3 meters by 3 meters. That means the cube is basically, it's almost 10 feet by 10 feet by 10 feet. So the size of a small bedroom. That amount of water per minute, that's a lot of water. So that's what's happening here. That water change of volume is constant, and the water is going to come up in the cone. So what I've done is I've written down water is filling a cone at pi meters cubed per minute. The cone has a height of 10 and a radius of 5. When the water is 7.5 or 15 house meters deep, how fast is the water level rising? So that's the question. So let me get rid of this part. Okay, now let's take a look at this cone. So it's a cone. The radius is 5. All right. The first step in doing related rates is to make a diagram. The radius is 5 and the height is 10. Now, that's the whole cone. But the water isn't filling that whole cone. The water on its way is doing other things. It doesn't have a measurement of 10 or a radius of 5. In fact, they want us to talk about what's happening here when the water in the cone is 7.5 meters deep. So that would be 7.5. Now notice that these two triangles, this one at 7.5 and this one at full height, are similar triangles. All right. Along the way, you'd have many, many other similar triangles. All right. But these two triangles are similar triangles. They're all similar, actually. And they come in such that the radius and the height have this relationship of the height is always 2 times the radius. All right. So the height is always 2 times the radius. All right. Or the radius is equal to 1/2 the height. All right. That might be a very important aspect as we get into the equation here. All right. Now realize if we have a bunch of water coming into the cylinder, at the bottom, the water rises very quickly because there's not a lot of space down here. But as we go further up in the cone, there's a lot more space to fill up as the same amount of water goes into it. So the rate of rise of the water is going to slow down. Right? It's going to be very fast at the beginning, and it's going to be slower at the end. All right. We're concerned with what's the rate of rise when the depth is 7.5. Okay. All right. So we have a volume situation. We have the volume of water coming in, and it's a cone. So let's write down, let's start with an equation. All right. And the next step in related rates is to say, oh, well, I have this diagram. Let me go with an equation that I know about a cone. So the volume of a cone is equal to, let's see, I think it's 1/3 times pi times r squared times h. Check that formula, but I'm pretty sure that's correct. 1/3 pi, yeah, that's good. So we have the volume of a cone. Now, another hint about related rates is do as much algebra as you can to simplify this first, and then take the derivative. But do not replace all your variables with constants now. Okay, because variables need to allow to be varied when we take derivatives. But we have a variable here for volume. The change in volume is going to be dV dt, which is going to be this pi amount of water entering the cone every minute. That's dV dt. 1/3 pi r squared h. Now r, do we need to actually deal with both r and h? Because if we do, we're going to have to use the product rule. And that's going to create more complication. Whereas what we're really concerned with in the question is how fast is the water rising? That's h. So let's see if we can get rid of r. Oh, we can get rid of r over here. Let's see, r is equal to 1/2 h. So if r equals 1/2 h, we can substitute. That's easy algebra. We can substitute 1/3 pi. Instead of r, we're going to have 1/2 h, or h divided by 2 squared times h. Okay, and let's simplify that also. Volume equals, let's see, h is going to be cubed now because it's h squared times h. So h is going to be cubed. This 2 makes this 2 a 4, right? We square the 2 and we get a 4. So we wind up with pi over 12. And the dogs are barking at something. Okay, so now we have volume in terms of just one variable. So we've avoided product rule. So that's going to be a little bit easier. And now we take the derivative. So the derivative, dV dt. The derivative in terms of time. That's what's going to connect our related rates, our dV dt and our dH dt, our change in height. dV dt, let's see, this looks like the power rule. So we're going to multiply a 3 times this. We wind up with 3 pi over 12, or pi over 4. Pi over 4. And then h squared. And then the derivative of the inside, following the chain rule, dH dt. Okay. Now we have something that we're going to be able to solve for dH dt if we can plug in the rest of the situations. Well, we were given dV dt. That's pi. Pi meters cubed of water is coming into the cone every minute. And then pi over 4 is pi over 4. H is 7.5, also known as 15 halves. So 15 halves squared dH dt. Okay, so if we square this, we wind up with 4 down here. So that's 16 down here. Well, here, let's do this. The pi comes out. If we get rid of this pi, we multiply by the reciprocal. So we wind up with 4 over pi times pi. And then this, we also are going to multiply by the reciprocal to the other side. So this 2 is going to wind up in the top as a 4. And this 15 is going to wind up in the bottom as a 225. And that's going to be dH dt. The pi's cancel, and we wind up with 16 over 225 dH dt. So that's a pretty small number. That's a very small number. Because at this point here, the radius is pretty large. This is a pretty large space. So you dump a bunch of water in here, the level doesn't really rise very far. What you'll notice is if you make this h number smaller, if you make the height smaller down here, then you're squaring a smaller number, and you're not going to wind up dividing by this giant number over here. So the rate will be faster at the bottom of the cone because of how that height winds up getting divided into the volume. So faster when the height is smaller, slower when the height is bigger, which makes sense. So dH dt is 16 divided by 225. Now that's going to be in meters per minute. Okay. We will do more of these. Hope this helps. Ask me in class, obviously, if it's not.